Okay, so today we will have session 2. Again, session 1 was a success, and I'm sure that session 2 will be also at least as good as session 1. It will be on management of desalinated water and brine and wastewater effluents. We all know when we have desalination, it's a process that removes salt, but again, it's not a process that degrades or breaks down salt. So eventually you're always left with a brine, and the brine can be a nuisance or can be an opportunity for valorization. So today we will hear about management of brines, because it's a nuisance, you need to do something with it, or some talk about how you can valorize some elements from the brine. So although you see 4 people there, we will have only 3 because Ori Lav from the Technion, injured his back, in one of the discs in his back, and he cannot move, so he canceled his flight. So we will have 3 talks. And after the 3 talks, we will have 5-minute break, bio break, and then we will have 1-hour discussion. And after the 1-hour discussion, there is a talk by Moshe Herzberg to replace Ori Lav, but because it doesn't fall in this theme, it will be after the discussion. So we will have 4 talks today, but 3 relevant for the discussion. So now, following the instruction, I need to introduce all the 3 speakers, and I will start with the first one. Dr. Daniel Kurtzman, or Dani. Dani is from the Vulcani Center Institute in Israel. He got all his degrees, BS, MS, and PhD from the Hebrew University in atmospheric, environmental, and soil and water sciences. He had a postdoc at UT Austin. And since, again, 2008, he's a researcher in the Vulcani Center. Dani's main expertise are managed aquifer recharge, nitrate contamination of groundwater under agricultural land, and soil aquifer phenomenon under various tolls and water resources of Israel. He's using many tools for his research, including field survey and monitoring of deep unsaturated zone, control lysimeters, experiments, groundwater field hydrology, and unsaturated and saturated flow transport and modeling. So this will be the first speaker. The second speaker we will have here, Aaron Wilson from Idaho National Lab. So Aaron is a chemist with over 20 years of experience in industry, academia, and academics and government laboratories. He was a PhD student at University of Colorado Boulder, where he worked on collaboration with a researcher from the National Renewable Energy Lab, which is nearby, and the Pacific Northwest. He went for a postdoc at Caltech, but also postdoc at the NIH. So very unique combination, Caltech and NIH. He has many publications and also 6 patents and 6 active patent applications. And since arriving at the Idaho National Lab in 2010, he has been active principal investigator and is currently the chemical separations group lead. His work ranges from fundamental solution theory to design of pilot water treatment systems. He has pioneered the use of solvent and phase change materials, probably be part of what he will talk about. And this work resulted in multiple recognitions, including 2 R&D 100 awards and technology demonstration at the White House in 2016. And the last speaker will be, for this session, before the discussion, will be Baoxia Mi from UC Berkeley. Baoxia is the Wood Calvert Chair of Engineering and Associate Professor of the Civil and Environmental Engineering Department at Berkeley. She received a BS and MS degree from Tianjin University in China, PhD from University of Illinois, and postdoc at Yale. She directed research and educational activities of the Membrane Innovation Lab, this is the name of her lab at Berkeley, studying physicochemical and biological processes with emphasis on advanced membrane processes and nanotechnology. Dr. Mi's achievements include the NSF Career Award, Hellman Fellows Award, CAPIS Nanova Young Investigator Award, and Baker Spark Prize. And now with this introduction, we have the first speaker, and it will be Daniel.
Oh, hi, everyone. Thank you, Avner, Manny, and probably also Gideon, giving me that opportunity to speak here. So I'm I'll speak on storage and remineralization of desalinated seawater in the natural subsurface. This is an ongoing project. I had many collaborators. I'd like to mention three of them. Yonatan Ganot was a PhD student in my lab and got his PhD from the Hebrew University of Jerusalem. Dr. Yoram Katz is a hydrogeologist of Mekorot, our national water company, which is a central collaborator in my research, and certainly in this talk, all the sites I'll speak about are run by Mekorot. And German Rudnik, who is still a PhD candidate in my lab, hopefully will get his PhD from Tel Aviv University. I collaborate with Avinoam Rabinovich there. As for funding, I must acknowledge the European Union for two consortia we were part of, and the BMBF MOST, the Israel-Germany Research Fund for Water Technology. Okay, so before I start, I'll speak a little about hydrology and managed aquifer recharge in Israel. So in the left panel, this is a annual precipitation map. So you see in red, it's the desert in the south, less than 100 millimeters per year. But in the center of Israel, we have between 400 to 600 millimeters per year. That's the green colors there. Well, that in the old days, that put us Israel at the western end of what's called the Fertile Crescent. And both in the old days and then nowadays, it supports two pretty good aquifers. And the one I'm speaking is in the black polygon, which we call the Israeli coastal aquifer. So in the middle panel, you see a soil map of covering this aquifer. So about half of the aquifer is clays, you see in brown, whereas the orange that covers about a third of the aquifer is what we call chamra soil. It's sandy loam to loamy sand. And the most important to our talk is the sand dunes in yellow that cover 15% of the area of the aquifer. In the right-hand panel, you can see the cultivated land in year 2000. And the most clear special correlation between the middle and the right panel is that no or hardly any agriculture developed on the sands. So what did develop on the sands is Mekorot, our national water company, took over significant areas over the sand and developed managed aquifer recharge system through infiltration ponds. So in the southern part, the Shikma near the city of Ashkelon, and in the north of the aquifer near Hadera or Caesarea, the Menashe systems. These are both systems for drinking water, managed aquifer research system. At first they were fed by floodwater. The two big sand dunes in the center, the Rishon LeZion sand dune and the Yavne sand dune, are used for soil aquifer treatment of Tel Aviv metropole secondary effluents, and these are operations that produce, like was said before, high quality irrigation water. So next development in the last 20 years, the 5 desalination plants you see in purple, and this changed the feed of the two managed aquifer recharge for drinking water. They added another source of water, which is desalinated seawater surplus. Sometime in the winter, we don't want the plant to shut down, and the plant manufactures the water, and there's not many users for it, so we store it in the aquifer. I concentrate on the Menashe site near Hadera, and let's zoom into it. So here on the right, you can see a geological map. So the yellow, the left down type, the yellow color is the sands I just show, whereas the orange or brown part is Eocene chalk that doesn't percolate good. And it doesn't percolate good as it forms a lot of runoff when there's heavy rains. And back in the 1960s, it was a waste. The runoff runs very fast to the Mediterranean, and we lose the water from the freshwater storage. Therefore, our clever hydrogeologists back in the 1950s, 60s put the dam in a 16-kilometer channel and moved the water to the sands, where it percolates to a good aquifer, and we can store it and use it then. So this operation it operates since 1968, and it on average gives 10 million cubic meters per year. And in the left you can see the histogram so it's very variable. In many years we have less than 4 million cubic meters per year, but also in many years we have also 20 and more from this operation. So, and then in 2010, the Hadera desalination plant started to work. And in 2014, for the first time, they also discharged some water in the winter to store it in the Hadera sands. So I'll zoom into it to the sands now here. So as you can see, the flood water comes from the northeast in the blue line, and to a settling pond first, and then to 3 infiltration ponds. So since 2015, we managed, it almost works perfectly, that the surface water uses the 2 northern ponds, pond number 1 and number 2, while the desalinated seawater is discharged to the southern pond number 3, as you can see in red. And this is how it looks when the desalinated water floods pond number 3. And we installed here some research apparatus, wells that goes down to the water table area, 30 meters, as you see here in the right hand, and some suction cups that the Ido is holding that bottle. The vacuum bottle, we can only suck from sand when it's pretty much saturated. So my talk is, we'll speak on these waters, and I'll speak on 3 topics. First, infiltration and recharge dynamics of this relatively high-quality water that is used for infiltration. Second part will be magnesium and calcium geochemistry in the variably saturated zone in this operation, and I'll also say something on magnesium and calcium in the Shofdan, much more intensive managed aquifer recharge site. And in the third part, I'll go into the aquifer while the water, after it percolates, it flows in the aquifer towards the purple points. You can see that these are the abstraction wells. And I'll talk about how can we predict the percentage of desalinated water flowing to these wells. Okay, so let's start about first with infiltration. So here you can see in the top the ponding depth of the infiltration event of desalinated seawater that occurred in January 2015. Luckily, the discharge was stopped a few times, and the decrease in the ponding depth, we can estimate the total infiltration rate of the pond. We also tried to look on spatial variability, so we had 24 single ring infiltration rings, and luckily the results were pretty much the same. The infiltration rates to the dry pond at the beginning of the infiltration rate was in the area of 10 meters per day, whereas after a few weeks of ponding, it went down to 0.4 meters per day. So we usually speak about clogging in these infiltration ponds, but for this high quality, very low turbidity water, that's probably not the case, and we didn't see any evidence for clogging. And what we did find is when we test the sediment structure, So these are sandy infiltration ponds, but they have also clay beds down in between 4 to 6 meters, as you can see here, which their permeability is much lower. So if you calculate the effective hydraulic conductivity or saturated hydraulic conductivity by this harmonic mean, you'll get the rates close to the rates I showed before that we measured. So if you assume a unit gradient and Darcy law, so you can calculate it easily by just knowing I won't say calculate, but estimate it pretty well, just knowing the sediment and having good samples of the sediment. So we fitted a one-dimensional variably saturated flow model to this section, and we fitted it to the entire pond infiltration rates. So you can see in the dashed black line, this is the infiltration rates, whereas the red line, these are the recharge rates. Yeah? So infiltration is the flux on the surface, recharge is the flux that goes down to the water table. So with this model, we calculate the temporal recharge to the aquifer. And so, and the next year, we use the next year event to validate, and it pretty well the dashed line hits a few observations that we have for infiltration of the entire pond. So to summarize this part, infiltration rate decreased from 10 to 0.5, 0.4 actually, within days of infiltration. Is it surface clogging? No. It's the low permeability layers of the unsaturated zone, and we can estimate the final infiltration rate from the sediment samples. And we calibrated a model that will be used in the next chapters. And this was published in 2017 in Hydrology and Air System Sciences. So the next thing I'll talk about is the geochemical evolution of the recharging water. And when we look on the geochemistry of the system, I look on the sediment, and then I'll talk on the water. So in the left you can see the sediment profile. We tested two geochemical aspects. First, the carbonate content. So you can see we have some carbonate in the top sand, and then in the lower sand it goes down, the carbonate is flushed. And deeper in about 16 meters depth, we get to the calcareous sandstone we call coca, which has a high percentage of carbonate. The gray profile is under exchangeable cations, is the cation exchange capacity of the sediment. And the two major exchangeable cations are the calcium and magnesium. Calcium, most of the profile is about an order of magnitude higher exchangeable calcium than exchangeable magnesium. So this is for the sediment. While the water, we divide three types of water here. First, the desalinated water. We call them post-treated desalinated water. Sorry, I think I need so the water, the desalinated water, post-treated by dissolving limestone into it. So the major cation is calcium, and the major anion is bicarbonate. And magnesium, as said before, the problem is practically zero. It's not zero, of course, no zero in chemistry, but it's 0.1, 0.2 milligrams per liter magnesium. Then we have the water we sampled from the observation wells that just go down to the water table area. So from the stable isotopes of water, we know this is the same water. It's not water from the natural aquifer. This is desalinated water that percolated. And it already has 2 to 3 milligrams per liter magnesium. It has more bicarbonate, and generally you see the total dissolved solids a little higher. The third type of water is the groundwater that we pumped from wells that are far from the infiltration pond and still didn't see the desalinated water. So generally they have more minerals into it. Generally the TDS is 3 times more than the desalinated water. The magnesium level in this area is 13 milligrams per liter, which is above the 10 milligrams per liter recommended by the World Health Organization for drinking water. So if we look on the calcium-magnesium ratio, so exchangeable calcium-magnesium ratio in the sediment, it's between 1 to 10, as you can see here, between the black and red profiles. Whereas in the post-treated desalinated water, it's much more. The low is 30, and the highest we saw is 120. Therefore, the direction of the ion exchange will be the calcium goes from the water into the sediment, whereas the magnesium desorbs from the sediment into the water. So this is the process we have here. If we look in the central panel, this is the top 3 meters results from suction cups we used, where the T1 is the first profile and T4 is the latest profile, about a year and a half between them. We see the magnesium is like an ion exchanger that the top 2 meters were exhausted in these 2 years of infiltration of desalinated water. And remember this trend for the next slide. We took these results and we put on the flow model I mentioned before, a transport model and a reactive transport model. And now the model we have 4 profiles here, 5, 10, 25, and 50 years of simulation. And the depth is 30 years. So, and what we can do in the model and we cannot do in reality is to take water that was not post-treated in the plant and to see maybe we can post-treat it by bringing the water to the rock and not the rock to the water like we do now. It looks cheaper. So the 2 reaction we calculated in this model is a calcite dissolution and precipitation and ion exchange. So in the left hand you can see that after 50 years we dissolve only about 2 meters of the calcite. So dissolving calcite and adding calcium from the sediment is sustainable for centuries. Whereas when we look on the right for the cation exchange, so if we look on the magnesium profile, we can see we pretty much exhaust the 30 meters magnesium profile after 50 years, and the same trend we saw for 3 meters in 2 years, we see in the model for 50 years and 30 meters. Okay. So if I summarize these parts, I can say enrichment of non-post-treated desalinated water with calcium and bicarbonate is possible through infiltration. It's cheaper, mostly environmentally. It's cheaper than industrial treatment in plant and sustainable for centuries. But the addition of 2 to 3 milligrams per liter magnesium through cation exchange will occur also with non-post-treated calcium. First, the calcium will be dissolved and the exchange will happen deeper in the profile. Nevertheless, exchangeable magnesium will be depleted within decades. And this was also published in Water Resources Research in 2018. Now, I jumped with calcium and magnesium to another site, to the Shafdan, more famous site. It works already more than 40 years in some in parts of it, and it's much more intensive. In the site I showed before, we have about a column of 20 meters of water percolating per year through the infiltration pond. In the Shafdan, which has much more infiltration ponds, it's about 120 meters column of water. So the history of water supply in Israel is kind of divided before desalination and after desalination. So let's look at the inflow to the Shafdan system before desalination. The inflow, the calcium level on average was 70 milligrams per liter, whereas after the soil aquifer treatment, the treatment added, the sediment added 30 milligrams per liter. Whereas for magnesium, Sea of Galilee water was the main source. It's pretty rich in magnesium. It was 30 milligrams per liter, but the soil aquifer treatment reduced the magnesium to 24. That means the sediment absorbs the magnesium. Whereas in the desalination era, most of the water that gets into the wastewater treatment plant is from the desalinated water, so the calcium is lower, but as you can see, still the calcium, the soil aquifer treatment adds 30 milligrams per liter calcium, whereas the magnesium is now desorbed from the sediment, and the inlet is 12 milligrams per liter on average, and after SAT we get 20 milligrams per liter of average. So the farmers that use the Shafdan water, of course, are happy with that. The magnesium level didn't change dramatically, and it's certainly enough magnesium. They don't have to add magnesium by fertilization. So this is an aspect of the Shafdan soil aquifer treatment that we're lucky, but it works pretty good for us. We charged it as an ion exchanger before the desalination era, and we are now getting the magnesium back in the desalination era. Okay, now I go back to the site at Menashe, and the third part of the lecture, I'll try to estimate the mixing of natural and desalinated seawater in the aquifer using stable isotopes. So I remind you the desalinated water goes to pond number 3, the southern pond, while the floodwater goes into the northern ponds 1 and 2. At the lower left panel, you can see in the bars the amount of water in the left-hand vertical axis that was recharged. In red, the desalinated water for the 8 years between 2015 and 2022, and in blue, the runoff water. So as you can see, until 2018, we were in drought. There were very little runoff water, and whereas after 2018, we have rainy years, and you see more of the blue bars. So this is a monthly discharge. So usually, like in 2017 and 2016, it was only in January, and in 2019, this operation was January, February, March. Okay. Now the colored curves you see there is the mixing ratio of desalinated water in the wells. So the yellow curve is for the yellow well here, M9, and the gray curve is for the gray curve, M6. And so M6 is the well that it's down gradient. Generally, the natural gradient is towards the Mediterranean to the west. So it's down gradient from the pond that where we discharge desalinated water. Therefore, it has the highest ratio of desalinated water, about 55%. And we calculate this ratio from the stable isotopes. The reverse osmosis process that does not change the stable isotope of the Eastern Mediterranean water, which is very high because of high evaporation. It's plus 10 promile. Promile is the units the hydrogeologists It's normalized units of the concentration of the isotope. Like, so it's plus 10 for deuterium, whereas the natural freshwater is minus 20, and we showed in this paper in HESS that we can use a 2N members approach pretty good to estimate the percentage of this desalinated water in the sample. So we wanted to investigate how can we predict that percentage, like for knowing how much magnesium, let's say we say it's non-reactive, so the mix will give us the concentration of magnesium. It's not exactly non-reactive, but it's in the aquifer, it's closely non-reactive. The aquifer adds a little, not like in the unsaturated zone that I showed before. Okay, so every problem like this, when we want to predict, we have some uncertainty, and we have here two types of uncertainty. First, we're dealing with the subsurface. We don't know the aquifer. How is the aquifer composed? We only know it from the wells we drill, but the wells are very small volume of the aquifer. So we need to interpolate the type of rock, the hydraulic properties of the rock. And we can do that in what we do in stochastic hydrology. We can make many realizations of the aquifer and run flow and transport model through these realizations and see the results. The second source of uncertainty is the climatic. As you see, it's very variable, the amount of water that will be available through the ephemeral flows. So we could also fit the histogram, actually the same histogram, but now in larger bins here. And we can fit a probability density function. This is a gamma probability, and make many realizations of the future available water through the runoff system. And so we wanted to predict here. Just a minute, okay. So we handled this numerical experiments. We had 4 ensembles of 30 realization each. I'll concentrate only on two, on the green ensemble and the blue ensemble. So in the green ensemble, we put 30 realizations of the aquifer. All realization fits the data from the boreholes, fits the statistics, and fits the spatial statistics, but still they're different. And we said the future available water is deterministic, okay? So we have one scenario of the future available water. While the blue realization, the blue ensemble is the opposite. We have a single realization of the aquifer. We say we know the aquifer deterministically, but we don't know the future climate and the availability of runoff water. So we have 30 realizations, each of 25 years of available runoff for managed aquifer recharge. So what you see in these panels in the center, so let's look on the center one. It's a well M9. It's a yellow well down in the left here, you can see. And let's look on the ensemble. The blue ensemble shows the percentage of desalinated water, 30 for every time we have 30 results of the realizations. And as you can see, it's very variable, and the envelope of results is very large. Much larger than the green ensemble, which is the structural uncertainty. So the climatic uncertainty is much larger in this system. In the right-hand panel, this is the coefficient of variation of these 30 curves. As you can see, the blue coefficient of variation is always higher than the green coefficient of variation. So I'll summarize this chapter. If the largest source of water is climate dependent, the climatic uncertainty prevails over the structural uncertainty for mixing predictions in wells close to the managed aquifer recharge. And the next conclusion, I didn't show it, but it's in the paper in Water Resources Research 2022. The uncertainty in mixing derived by climate variability decreases with distance from the recharge location, whereas the structural uncertainty is stable with increasing distance. That means that if I will take not for the closest wells from the infiltration ponds, but wells down gradient 2 kilometers, so the blue ensemble envelope gets smaller, where the green stays the same. So the structural uncertainty relatively will grow. And that's it. Thank you.
I don't get a laser to point. Hi, I'm Aaron Wilson. I'm with Idaho National Laboratory. I think Manny, thanks for the introduction. It's really cool to go after Daniel. I'm also going to be talking about something a little different, and that's using solvent-driven processes to recover minerals. And I'll be doing this more from a critical materials type perspective. I'm a researcher with the Critical Materials Institute, which is a DOE hub. Their meeting actually starts tomorrow, and I'll be sticking around here and showing up there late. I'm also the center lead for something called Metallic, which is a DOE infrastructure investment of $75 million into developing kind of a user facility for critical materials research. That's just getting kicked off now. There's a good chance you've never heard of Idaho National Lab. Like, no, we're a bit of a secret. We used to be a plot of land about the size of Rhode Island that has a bunch of cinder cones on it that was owned by the Navy, and they take guns for the ships in the Pacific, and they'd take them out to Idaho, and they'd retrofit them and shoot them at the cinder cones, at the old volcano cinder cones, and they'd sight them. And when they decided that they were going to start building reactors, they said, like, well, we did one near Chicago in the squash court. Maybe we shouldn't keep doing that. And so they moved the reactor construction out to Idaho. And we've had more than 50 reactors on site. Does that say that up there? It might. We've got about 6,000 employees. We've got 3 missions. We're continuing to do nuclear power, so the plowshares aspect of nuclear power. We're not a weapons lab. We have a very strong cybersecurity element, which is really kind of amazing, but I can't say anything good about them or at least no real examples. And then energy environment, which is where I fall. Fun place to work. So right now, we're kind of in the midst of transitioning from a global society run off of fossil infrastructure to one that is going to be run through critical materials. And this is a big transition. We're going to be collecting, storing, and utilizing all our energy basically through materials, whether it's a reactor or a solar panel or a wind turbine. This is hard rock materials, not coal, not oil, not gas. And so we need to improve how we get those materials, both from primary source, how we process them, how we recycle them. Ultimately, for people, this is going to be lower cost. I mean, like, just from shooting from the hip, cars are going to cost half as much, and it's going to cost a quarter as much as it does now to power them. This is going to be a huge savings for the consumer. So a quick tutorial on what it takes to mine. So it's really the same whether you start from ore or secondary recycled material, e-waste, like hard drives, car batteries. You collect it, you crush it, and then you physically separate it, because each little tiny bit of rock will have more ore or less ore than another. Then you go from those solid-solid separations to solid liquid. So that's leaching. Leaching's done in many different ways. It's not just throwing acid at it. Sometimes it's throwing acid and peroxide at it. Or you smelt it and get it into a liquid that way. Then you hit liquid-liquid separations, and that's what a lot of us here are very, very familiar with. You have a liquid rich in one thing, and you want to separate it into either a pure water or do selective separations. And then you ultimately need to take that liquid and get solids out of it if you're going after the material, the minerals and whatnot. And that can be electrowinning directly to metal from aqueous solutions such as copper. That's where a lot of our copper comes from. It might be smelted, but then it's electrowon. It's put back into an aqueous solution, pulled through the aqueous solution, and then reduced back to metal to get the purity we need to actually do electronics. Anyways, in these processes, we put in mechanical energy, we put in water and chemicals, as well as thermal and electric energy. And out of this comes tailings, as well as some really complex wastes. Brines, if we go for brines, can bypass a lot of this. Like the Red Dog mine up in Alaska is the biggest waste generator in the United States. And that's because once they pull something out of the ground, you got a lot of rock that's now just waste. So there's all these processing steps that have real water management issues with them. And if the water management issues are not addressed, there can be terrible, terrible, terrible outcomes. That's $15 billion Brazilian, actually. But this is important. That's 43 million cubic meters of tailings that killed 19 people. And the Brazilian government just levied, that's 15 billion Australian, because Australians report on it, which is equivalent to 9.7 billion in US dollars. But the cost to treat that water would have been $500 million. So they didn't to do it dry, and by treat it I mean dry storage, take it from a tailing to dry storage, because it cost about 10 cents to throw this stuff into a tailings pond, whereas $10 to go to dry form storage. And right now this is a filter press is the general technology to at least partially treat it. But this is a place for innovation. And this is a big issue. These slurry ponds are problems everywhere. About every 2 years or so, based off of what I can find, there's a major slurry pond failure. And this is not just this is not like rogue operators. These are the majors. These are the most significant mining companies out there, the BHPs, the Glencores, the Vales, the Rio Tintos, the various ones. And I mean, they're all the ones I have stuff up here for variety. So I have another iron ore failure up at the top. I have red mud, which is bauxite residue, which is more midstream processing. Then you have coal fines, which is soft rocks. That's actually the largest volume. And then you have fly ash. And the significance of the coal fines and fly ash is those are both U.S. based, whereas we've pushed most of our other mining offshore. This is a big deal, though. And it'd be one thing if research was being done on this, but this is research for a range of communities. You see pharmaceuticals are putting a lot of their revenue into research as semiconductor software. And I mean, just the S&P companies in general. But mining is currently at less than 1% of their revenue going into research. It's just not happening. There's just not progress being made. And I think this is worth acknowledging. When I found this out, it was shocking. Something else that is happening is this is not a free market. You can look at the top. This is from an IEA report, and you can see at the top that the top 3 producers of oil and natural gas come to about 40% of the total market. United States, Saudi Arabia, Russia dominate that space, but they add up to 40%. Minerals are being harvested basically where they are around the world, but they're all processed in China. China's processing the vast majority of these, and this is strategic. This is intentional. This is being done on purpose at a national level. So, one thing I wanted to hit on was this issue. Megan talked about climate change. This is a huge climate change issue because these are designed with an expectation of how the climate's going to be, and if that's valid, it's anyone's guess. Based off what it looks like, there might be greater risk in the future. But this, Shihan, you put this up there. I put this up there. Manny published it originally. We're closing in on basically where we can't get better at desalination. And so I'm not the only one that's pointing at this, but maybe we try to stop thinking about this as like an infrastructure cost to manage. Like, that's not the right way to think about it. Maybe we can transform this into a revenue generating space. So a mineral resource and processing industry. And this has too many words on it, so I'll just keep talking. But we have lithium, this is the Berkeley pit in Butte, Montana, and that's just some nickel sulfate. What this actually looks like in kind of real terms. So I use Carlsbad kind of as like a volumetric proxy for this. So 140 million cubic meters of seawater coming in, 70 million cubic meters of water per year. It requires 30 megawatts, which is really not that much electricity. It's actually, I work at the Nuclear Energy Laboratory. This drives the guys who make nuclear power plants nuts. They want something that sucks a lot of electricity, which is part of the reason I have the second line down there. So if we go to the point where basically there's a kilogram of magnesium in every ton of seawater, rule of thumb. So there's 140 million tons of magnesium in that. Now, if we take that all the way to metal, you're using at least 20 times the energy. We can do all sorts of things on exergy and thermal versus electrical. But you're going from about a cost of $35 to $70 million a year using the cutting edge, state-of-the-art, 30 cents per ton seawater desalination to something where you're generating revenue on the order of $300 to $1 billion a year. So, and it doesn't have to make that much money. It just doesn't, it can't cost anything. So the water becomes a byproduct of something we all need, a structural material, a replacement for aluminum and iron. And just to sing the praises of magnesium, it's 33% lighter than aluminum. It's easier to recycle than aluminum by 50%. Carbon fiber, I just like to remind people, carbon fiber requires low-paid people to put it together because it's a labor-intensive layup given current technology, which means that's why we haven't seen it replace huge swaths of structural material. You have to have people to do it. It comes from many sources. Ocean is just one of them, and the value of it has been stable over the last 20 years. $2 to $7 probably favor the lower end to be realistic, but the aluminum to magnesium ratio is a real economic factor, and it can ship anywhere you want to ship it. And if you go to Home Depot, if you go to the store right now, the premium tools will all be magnesium house tools. So there's again a rise in magnesium use. But again, there's a story here. So back in the 90s, we made magnesium out of seashells and seashells and seawater down in Freeport, Texas. That's the purple bar in this graph. That's Freeport, Texas, and the brown bar is someplace in Norway. But this is seawater. And then in the mid-90s, China decided that they were going to make it out of coal and dolomite. And they took over the market. They drove the price of magnesium down. And once everyone else went out of business, the price of magnesium came right back up. So historically, we've made magnesium from seawater at a cost competitive rate. And we need magnesium for all sorts of things, including producing steel and aluminum. So it's a real interesting situation. This is a really interesting figure. So the one on the left is the concentration of minerals in seawater relative to the products that you can make out of them. So you see on the far right, they're barely visible, but you have sodium chloride, HCl, and sodium hydroxide. They have different values. Now, the potential to mine something from seawater is the perpendicular offset from one of those diagonal lines. I don't really love that. So I multiplied the x-axis by the y-axis, which ends up being the value in a cubic meter of seawater. So then the real potential is just the vertical offset. So the higher it is on the graph, the more valuable it is. I'm from Idaho, which is right near the Great Salt Lake, so I've also got the Great Salt Lake on this figure. But if you notice on the right, you've got sodium chloride, you've got HCl, and you've got sodium hydroxide. Those you could flood those markets, no problem. You could destroy the value of those commodities any day of the week, any place you put a desal plant. They're not going to have value. But magnesium is the next one there. And the magnesium it can go any place. You can ship it around the world, and the market can absorb, the market could absorb all the desal magnesium that's out there right now. And once you've pulled the magnesium out, then you can start looking at other things. You're going to have concentrates and byproduct streams. You could have a potential 10K enhancement after desal and magnesium recovery, where you could really start looking at the uranium in the seawater. You could mine the gold in the ocean, which we've all heard about so many times. But this plays into a mining truism that grade is king. The real value of any activity is going after the highest grade ore you can, and that person who does that is going to make the most money, and separations are largely irrelevant because we all have the same ones, which runs counter to a lot of what we kind of hear from the water treatment folks, where we're going after extremely dilute sources. In my mind, we should look for active recovery and sequential recoveries, where we grab a high value. I'm working with the people in Butte, Montana. People want them to go after the rare earths in the Berkeley pit, but they're like, we're going to have to hit the zinc in this first to make it profitable. Then we can consider the rare earths, and we need to listen to them. You work down the sequence of value. In China, they actually mandate that if you dig it out of the ground, you have to pull the gallium out of the aluminum bauxite. We don't do that. But since it's mandated there, it's dropped the value out of the market, and they're the only ones to produce it. So it destroyed the rest of the market in the process. Okay, let's see. Okay, there we go. Okay, so we've actually seen a figure a lot like this already once or twice. But where I'm working is basically here. So NF is, I always thought NF was a damaged, expensive RO membrane. It's like, that's what it is. But we're to the point where we're really seeing it kind of hit commercial application a few places. It's replacing UF in a few places. What that gives you is a divalent stream and a monovalent stream, or something close to it. That's something I can really work with. I've got a technology where solvents induce precipitation of solids out. That's the DME, dimethyl ether fractional crystallization. So I don't need to evaporate that to get to the solids. I can just do my thing, and the solids come straight out of solution. I'll show a little bit about that. But then across the top, you can imagine you've got seawater RO, you've got osmotically assisted reverse osmosis, or you could have high pressure, you could do both. And then I've got a technology called DME water extraction, which is a zero liquid discharge process. But this basically lets you get to the minerals in this water, with a seawater or some other water. Yeah, and we're working on these technology yet. And so I'm working on a solid liquid separation. And the most established technologies, the real technologies in this space, are evaporative crystallization, which is massively inefficient. Shihong put up some good data on this. You have chemical precipitation, which is actually a fabulous technology. Lime softening is amazing. And in many hydrometallurgical pathways, these chemical precipitants are actually recycled in the system, which are fabulous as well. We should stick with those guys. But oftentimes, you end up with a brine waste product if you do it that way. What we're aiming to do is do a cycle, a chemical trigger, and get solids out in a depleted solution at less than 95% energy savings, with no chemical consumption and no increase in the waste. And just to highlight the cost of crystallizers, this is a battery recycler in the U.S. Crystallizers have to be shipped from a handful of places. They're very poorly scalable. They have to be built at the scale you want. Reverse osmosis is awesome. You can do a little bit, and then you can add more, or you can build it to the exact scale you want. This is not a good technology. This is like the third root law gone awry. It's expensive equipment, It's expensive material, it's large scale, and costly to operate. So what we have is we have dimethyl ether-driven water extraction. So if we take 15:1 ratio in mass DME to water, the water will go into the DME, and you'll end up with dry solids. If you do this with sodium chloride, you end up with about 250 parts per million sodium chloride in the final product. That's less than Gatorade. Just as a reference point, you end up with 20 parts per million DME. DME is approved for food processing in both the US and Europe, and it's not a greenhouse gas. It decomposes very rapidly in the environment, and it is classified as a peroxide former, but all experiments point to the fact that it doesn't actually form peroxides. It's just an ether, so it gets cataloged in that group. Anyways, I worked with John Leonard and Zihao Fu, and they did some calculations, and it looks like we could go to ZLD for the cost of MED. And this is a mixed, I think this uses 50 degrees C heat. We can actually operate with a temperature differential as long as it's above negative 22 degrees C. DME is a refrigerant, so all it needs is a temperature differential. But this is exciting, but what's even more exciting is we don't need 15 times the DME as water. We could actually do half an equivalent of DME for one equivalent of water and drive things out of solution. That's because when you put an organic in an aqueous, things precipitate out. How much precipitate out varies a lot. We get between 12 and 99% recovery, which could be 3 to 70 grams per 100 mils of solution. This is a purification step done correctly. We get separation factors anywhere from 1, which is no separation, up to 700, which is a good separation. These are some quick examples. Top right, the one on the top is a 4-centimeter cobalt sulfate crystal from actually a recycled magnet, a cobalt samarium magnet. Then you have industrial nickel sulfate from battery recycling. It says greater than 70%. We actually get 95% recovery. You got some neodymium crystals there. You got calcium sulfate softening, basically. You got ZLD. I don't think I get into it, but we can change the temperature of our system and go from 99.5% lanthanide sulfates to 99.5% transition metal sulfates. Really cool. You can do that with evaporation. That's the sodium-potassium separation. But this just works well. And we can dry solids, which is kind of what I was talking about first. Okay, I have a moment. So this just gets into the historic connection between water and energy. So Alcoa planted the largest aluminum factory in the world in the Tennessee Valley Authority during World War II because of the water and because of the associated energy. Oak Ridge got put there as well for the exact same reason. Oak Ridge eventually led to nuclear power, and then we ended up having a nuclear power plant in the Tennessee Valley. It's just this, as the DOE, this is something I like to highlight for a lot of our sponsors. There's just this is the water energy nexus, it exists in multiple ways. And then I also want to highlight, I don't know how to pronounce his name correctly because I've read his name a million times, but I'm one of those people that's just read his name. Zav Alfasi. So he's a researcher at Ben Gurion University. He was in the nuclear engineering department. He was interested in separating various salts from in like nuclear applications. There's huge amounts of overlap. Like hydrometallurgical separations were invented for the Manhattan process that are applied to many things these days. Anyways, he wrote a series of about 8 papers on solvent-based precipitation of salts that were basically the foundation of my work with DME. The real innovation that I was able to dig deeper into what he did, but the DME is something we can recover 99.9995% of it in 10 minutes. That's the real key innovation that makes the DME possible, is that we don't end up with DME in the product water, in the concentrate, in the solids, which you do if you're working with amines or other polar organic solvents. Anyways, his work is the work that allowed me to get started in this space. We're building up to larger scales. And I don't have a conclusion slide, but this is the vision. We pump lixiviant into the ground to leach out material. We pump a solution up for in situ / solution mining, and then we do a process that doesn't change the salinity of the water to get the minerals out. And this applies to a lot of things. But anyways, I've got a great team too. And I will hand up.
Well, it's definitely my pleasure here to present some of our work on interfacial solar evaporation. It's very nice that my talk directly follow what Aaron's have been talking about in terms of mineral recovery from brine, because my talk is also kind of looking at this brine treatment from the other perspective, maybe more integrated with water recovery as well. So this must be designed by Manny on purpose, because even though my lab is called Membrane Innovation, I'm not going to talk about membrane process at all. So he asked me to talk about interfacial solar evaporation, the work that we have been working on this topic. So that's that. I think this community is very familiar with brine. Brine, we all know as a waste stream from a lot of industrial processes in terms of, like, for example, desalination plants, mining industry, gas oil drilling, and power plants. And we all know that the brine disposal could be problematic because it causes a lot of environmental concerns. And therefore, it could be very costly to manage the brine. At the same time, we all know brine treatment is expensive too. Tone and Alleviating have this very nice paper a few years ago. They did analysis of zero liquid discharge and explained why brine treatment is so expensive. It's largely due to the high salinity that we have in this waste brine. So if you look at this graph here, it clearly shows the specific energy in terms of water recovery from different sources of water as a function of salinity. So you can see that RO is actually down here in this graph. So it has, we all know, like the energy intensity of RO desalination process in terms of seawater is mostly in the 3 to 5 kilowatt-hour per cubic meter. But when the salinity increases, the energy intensity also increases accordingly. And we are currently lacking a technology that can really allow us to do this treatment of brine that has higher salinity than 2 times of seawater, which is the 70,000 ppm that is listed in this graph. So how do we do it? But before we start talking about specific technologies, I want to show, like maybe look at this brine from another, like more beautiful side. So we all know that we have a lot of natural brine lakes, and people are interested in these lakes not just because of the beautiful color. So they show different colors because the speciation of the minerals in this water, their concentration, as well as, of course, in some cases, the microorganisms that are growing in those water. People are interested in these brine lakes because there are a lot of critical minerals that we could potentially produce from these brine water. So, for example, people have been looking to producing critical minerals such as lithium, magnesium, nitrate, and also the examples that you have seen from Aaron's talk earlier. And in many of these kind of practical processes people are currently using to produce the critical minerals involve a process called solar evaporation ponds. So those are the pictures that the ponds that you see here. Of course, this is an AI-generated picture. It's not a real picture. But basically, people are using this solar evaporation pond to evaporate water, to concentrate the mineral to a point where we can economically precipitate the chemicals out or use other treatment to really produce the mineral. So, so this is, again, not a real picture, but there are real pictures out there. And if you are traveling around from airplane, it's not hard to find views like this one here, right? So this is an example of the solar evaporation pond on the Great Salt Lake in Utah. And the company Compass Minerals is using these solar evaporation ponds to produce potassium sulfate and magnesium chloride. And I think recently the company mentioned they also have like a reasonable concentration of lithium in these ponds. So they are also looking to the recovery lithium from these water. At the same time, also again, this here is a real picture of lithium fields in Chile. So this is this solar evaporation ponds were operated by this leading mining company SQM, who are producing obviously lithium from this brine that they have. Well, the water evaporates away, lithium concentration increases, and you can see actually the beautiful color change, the color change from turquoise to yellow. However, this is a natural process they are trying to use, and it's very, very slow. So the solar evaporation ponds takes almost 1.5 years to really allow them to get a concentration high enough for subsequent recovery of lithium from water. So it's an extremely process. And that's how it leads to the technology that I want to discuss today is the interfacial solar evaporation, how it's possibly allow us to significantly accelerate this process and to make it more economical. And also when Aaron talked about these hazardous effects, the flooding, all this other side, like a kind of negative side about this solar evaporation ponds, then by shrinking the timelines of this process, maybe we can control the process a lot better. So that's, with that, also I want to use this as, by no means I'm presenting a mature or good enough technology that can be used for now, but I also want to use this as an opportunity to discuss how we could maybe re-examine the brine treatment by integrating the water recovery aspects and the mineral recovery so that maybe possibly we could, instead of always treating the brine treatment as like the brine as a waste stream as a highly energy intensive process, maybe now we can look at it, shine it on a more positive light where we could potentially recover some valuable products from this process. So the technology I want to introduce today is called interfacial solar evaporation. It is basically to use a solid light absorber. So it absorbs sunlight, it generates heat, and then we localize the heat at the very interface where water will evaporate. So in this talk, I want to discuss how this interfacial solar evaporation could potentially accelerate the water evaporation rate, and also how we might engineer the material that we use for the solar evaporation to really allow some like a mineral recovery possible. So that's the goal of my discussion today. Interfacial solar evaporation is not a totally new process. People have been studying it since since 10 years ago. I arbitrarily just attribute it to the evolvement of the technology into 3 stages. The first generation, so it's like when it first started with some material scientists discovering these plasmonic nanoparticles that can absorb light and convert it to heat, and then they observe this a faster vapor generation from this particle surface. And then from there, people looked into other morphologies and other materials to make this process. And I consider the second generation of this process, this technology is people use materials to make a membrane. So this is more like a membrane, a porous material where water can be transported up, evaporate from the membrane surface, and then the salt crystals could accumulate on the surface. So that's we call it two-dimensional kind of films to allow this interfacial solar evaporation to take place. And then more recently, a lot of researchers have been looking into a three-dimensional design for this process. And there are some advantages of using this 3D structure, which I'm going to show you soon. So that's a little bit of history. And our lab really started with this process by synthesizing this two-dimensional membranes, porous membranes. At that time, because when we first looked into this technology, our goal is actually for desalination. So we were looking at mangrove trees, for example. We think, oh, this is a tree that can grow in really salty water, and they allow water transpiration to take place relatively efficiently. So maybe we can mimic this process, and that's why we call the graphene oxide material that we synthesize, we call it leaf. So we are trying to mimic this process, and so we synthesize this kind of membrane-like material. It's porous, and then we use it as the interfacial solar evaporator, and we have a water transporter to just suck the water by capillary force and lift it to this membrane to supply the water that is needed for evaporation. So and this is kind of like a picture of the structure of the 2D graphene oxide leaf. And you can see it's very porous. It's just like a macrofiltration membrane. But because of the graphene oxide is dark, it's black, as you can see here, and therefore it can absorb natural and solar light very efficiently. And these porous surface provide high surface area for evaporation. So that's the material. And here is just the water evaporation rate. As I mentioned earlier, our goal is to use this to accelerate water evaporation. And here you can see that when we have this like a tree structure, so the geoleaf separated from the bulk water, it can really enhance the water evaporation rate compared to the natural solar evaporation. But another important step I want to mention is the separation between the evaporative surface and the bulk water, because this separation is actually very critical. It minimizes the heat loss through this bulk water back into. So if we compare these lifted structure with versus the one that just floating on the surface, you can see almost like a double enhancement of the water evaporation rate. That's because the separation of the evaporative surface and the bulk water. So that's one critical factor. And of course, we also looked at other kind of materials to do this job. This is another study that was done a few years ago by Lin, who was a visiting student in our lab. She synthesized this reduced graphene oxide coated on nanofibrous hydrogel. And this material can work even better than the graphene oxide film that I talked about earlier. So this is a very interesting material. If you look at the dry material, it's white. But then once you put it in water, in contact with water, it absorbs water very fast, and then it becomes black. And then it absorbs sunlight and allow this solar evaporation to take place very efficiently. So when she compared this performance with other studies at that time, and this is one of the best performed material at that time. But this is by no means that the best material out there. My point is actually different. So if you, we also look into the water evaporation mechanisms to see why this interfacial solar evaporation is much more effective than natural water evaporation or evaporation from bulk water. So we actually use a combination of DSC and TGA to measure the evaporation enthalpy for the water evaporation from the membrane versus the bulk water. So for bulk water evaporation, it has a value of 2,300 joule per gram. But if you look at the enthalpy for the evaporation from this material, it actually becomes a lot lower. And our hypothesis here is that because we are allowing this water to really evaporate from a macro kind of a nanochanneled surface, it means that when this water is in this nanochannel, because the nanochannel, the material really interrupt the hydrogen bonding between water molecules. So we think it's easier for the water to just leave the surface as water clusters instead of single molecules. And that's probably why we observe this lower enthalpy value for evaporation from surface. But with this data, my point here is really to say that the material itself, it doesn't matter that much. If you can produce, as long as you can produce a macro power structure, it's black, that is efficient to absorb sunlight, you can basically observe very fast evaporation rate. So that means it's actually, there are a bunch of materials and a lot of studies on this, and they all work pretty well. However, I do want to go on to start talking about some other kind of maybe more engineering aspects of this process to make it work even more efficiently. So we all know, like, our target is to use solar light, and we all know solar actually moves from morning to noon to the evening, so we have this directional change. So it's not hard to imagine that if we have a flat surface, the effectiveness of collecting the solar light would not be as effective as the surface that is more vertical or have a different omnidirectional. So that's the kind of motivation why we want to design a three-dimensional structure to do this job. And of course, there were studies already using a lot of different three-dimensional structures. There are cones, there are cups, there are even mushroom structures, blocks. So people are studying all kinds of three-dimensional structures for solar evaporation. And we try to see what morphology or what kind of shape we want to use. Because another important factor in this consideration is to look at the lifting rate. Because when we have a three-dimensional structure, we need to lift the water up to a certain height. So the lifting capability of the structure will also limit the evaporation flux as well. So it's kind of like a balance between the water lifting capability of the structure and the amount of surface area that you can get from the structure. So that's an optimization process that Casey went through, and he determined that the best structure among the structures that he studied is this cylindrical structure. So that's how we synthesize this, what we call 3D stock for the study to compare it with the two-dimensional geoleaf that I mentioned earlier. This material is really, again, the synthesis is very simple. We just use a cotton stalk, and then we coat the same graphene oxide polymer mixture on the stalk. You can see here from the picture, in the middle is still uncoated cotton material. This is to keep the channel in the middle to open so that water can be lifted from the middle. And then the outside is coated by this graphene oxide polymer material for effective evaporation. So that's That's the material that we use. And first of all, I want to show like how this evaporation flux that you get from this three-dimensional structure could be a lot faster than this two-dimensional material. So of course, it also depends on the head that we use. And this, the EAI is basically the evaporation area versus the projective area. Of course, the taller the stock is, you get more evaporative area, and you get higher flux, and the flux could be a lot higher than the two-dimensional material. But this is not the only benefit. When we really examine the different conditions that we use during the evaporation process, we found some additional benefits. Of course, the response to light is one kind of, that's the original motivation. And we did find that with this three-dimensional structure, we, especially like if you look at the zenith angle, it means the angle like where the sun has moved away from the noon position, like the vertical position. You can see that the water flux actually increases when we have, like when the sun moves to evening or noon position, is because the effective collection of the solar light when the sun moves. So it's just a high evaporative area. And then we also look at the wind speed, how that affects the evaporation rate. Here you can see that when the wind speed increases, the two-dimensional membrane, the evaporation flux increased slightly, but you see much, much more dramatic effects from the wind speed increase. That's because, again, due to the 3D structure, it just creates more evaporation from the surface. But the most important benefit of this 3D structure is actually shown here. What we found, we all know, like for people who study evaporation, we all know like increasing salt concentration actually decrease the evaporation rate from natural water surface, natural evaporation. And the same thing that we observed with the two-dimensional material, you see this decrease of water flux as an increase of salinity. So here we studied the salinity up to like 17%, which is almost 5 times seawater concentration. And obviously, two-dimensional membrane, you see a lower flux. But interestingly, we didn't see any flux decrease at all with this three-dimensional structure, which is still something that we haven't found a perfect answer or explanation yet. We think it's related to the balance of salt transport within the 3D structure and the accumulation of salt on surface. But again, we don't have a perfect answer to explain why the salt concentration increase doesn't decrease the water evaporation flux at all. And another thing is that I didn't show the data. We actually run the experiment for a long, long time, like for days and days, allow this salt really accumulating on the surface. And with time, you can see the salt accumulate, they grow, they fall off from the stock surface, and you don't see a decrease of water flux at all. So that brings the excitement about this work, which means that we could potentially use this process to really, because it can evaporate the water so much faster, we could potentially use this to either shrink the surface area of evaporation pond by having all those benefits that I mentioned earlier. So the idea is that, for example, if we were to use solar evaporation to treat the brine, we could potentially have a floating structure like this. And we could possibly, because of the high evaporation rate, we can have a much smaller area. And also the smaller area will allow us to engineer better water vapor collection process to couple it with condensation process for water production. At the same time, we could potentially collect the salt. And then and that will allow the mineral recovery from this process. However, my story just doesn't stop here. I have to mention some challenges with this process as well. So because the data that I presented earlier are just with sodium chloride, and that's also the case in a lot of the literatures that you find on solar evaporation. Even though when they claim that it's resistant to scaling, that's the same phenomena I presented earlier with sodium chloride salt. Rarely, and there are not that many studies to really look into a mixture of salt and also the effects of other ions on this process. So Aiden is a new PhD student who studied a couple of years ago, and he picked up this work and started looking at the effects of divalent cations on this process. And here is what he found. So here is just a pure solution of sodium. It's all chloride salt. So it's when we look at sodium and potassium, the flux are pretty high. But then once he used calcium chloride or magnesium chloride, all the same concentration, and you see this dramatic decrease in water flux. Of course, this is run on a scale of like 10 days or so. And that really kind of discouraging, because when we have in the brines that we talk about, in most cases, we have a lot of this calcium, magnesium ions in it. So we try to understand what is happening here. This video shows the 10-day experiments, how you see the salt accumulating on the surface for the sodium and potassium. So you started seeing this crystal accumulation on the sodium and potassium at the end of 10 days, but you don't really see anything at all for calcium and magnesium concentration of solutions. And this is the picture of the stock at the end of the experiments. Again, for sodium and potassium, you see a lot of salt accumulation, but for calcium and magnesium, you don't see salt accumulation at all. And then when we look at the inside of the stock, this is the picture, kind of we cut it open and look at what we have inside of the stock. You can see for sodium and potassium, even though there are some crystals within the structure, but the structure is pretty much still open, and that will allow water transport. But for magnesium and calcium, it really blocked all the openings. So you see these almost like a gel-like structure block all the water transport within the stock. I think that's the reason. And indeed, when we look at the water transport, even without evaporation at all, we use this dye to show how tall the solution can go. You can see that in the middle for sodium and potassium, the dye and the water can really be lifted up to the top of the stock. But for calcium and magnesium, it just stops there. And then, of course, you can say, oh, you use very high concentration. Indeed, the 10% means 100,000 ppm. It's extremely high concentration that we use in the experiments. But even with lower concentration here, we tested a mixture of sodium chloride with a smaller concentration of calcium and magnesium. We observed very similar effects. And we also tested a realistic brine with a mixture of the salt is somewhere here. So it means that these divalent cations could really affect the evaporation rate. Again, this video is to show the accumulation of salt with the mixture. So you can see with the presence of calcium, magnesium, even the sodium chloride cannot precipitate out anymore. So that's very dramatic effects from these divalent ions. And then you can see here, basically when we cut it open, we see these minerals within the stock to block all the water transport. This doesn't really kill the technology yet. Even though I show very kind of smaller evaporation rate, this is still a lot faster than natural water evaporation. But still, I think this is an issue that we have to address. We have to be careful when you look at literature in this field to really pay attention to whether or not people have really used realistic brine to test it out, because there's kind of blocking effects that you could potentially have. But this is also another kind of possibility. I want to mention here is that I don't have that much time, but it's a possibility to really engineer the material to achieve some interactions with the ions in the water, and potentially, if, for example, if we could engineer the material to absorb lithium, we could potentially keep all the lithium in the structure and evaporate the salt out. So it also shows some promises or potentials to explore with this more negative effects. I will just skip this. This is just a review paper put together by Professor Jia Zhu from Nanjing University. We kind of co-authored on this perspective to show how solar evaporation could be potentially used for different types of applications. Finally, I want to summarize my talk by saying, hopefully, I show that interfacial solar evaporation is a promising technology that could be potentially used to integrate the water recovery and mineral recovery from brine, even though there's still a lot of work to be done, a lot of understanding to achieve before this technology become really, can go into real application. So finally, I just want to thank the student. Dr. Casey Finnerty was the one who did most of the work. He's a professor at UC Davis now, and Lin is the visiting student who's also a professor in China now. And then currently, Aiden is the student who picked up on this project and working on the avalanche Kaitan effects. And also have collaborators, and Dr. David Selleck was involved in some of the work, and Jeff Urban from Lawrence Berkeley Lab was involved in some of the work, and also some of the funding sources for this work. Thank you.